Hi, everyone. How are you doing? We have a few minutes before we start. Hello, Sarah. Hi. Yeah, it is dinner time right now, right? When I used to be on campus, I would bring snacks to class all the time because students would come off of work and they would take my class. So usually I have like chips and all kinds of goodies. But because of COVID, we can't have anything virtually. So maybe when we come back and everybody is safe. Hi, how are you doing? So while we wait, we are just gonna check out our assignment for today in our notes. And then I'll give everybody a couple more minutes to join us. And I'm gonna try to work through all the assignments that you submitted. I only have a little bit left to go. So it's already week 4. Wow. Before you know it, we will finish the semester, have summer. So I think summer schedule is going to come up pretty soon. We're wrapping up this week to submit, and then you should be able to see your summer schedule or the available courses by April. And then the fall, we're wrapping that up in April. And so that should be available in May or June for the fall. So they're discussing on whether they're going to bring back all 75% of the classes in the fall. So just keep in mind that some of the classes will go back to the campus once, everything is in order with the county. Okay, so we have a minute. Check out Canvas, Unit 4 module. I will post the videos on there as soon as they're ready. Okay, so it's 6 o'clock. I'm going to go ahead and get started. We might have a few people coming in a little later, possibly because of work. So welcome back. We're going to go through our next unit, and this is where the fun begins after all of the. So every week is going to be a little different, but for this week and next week, we are going to spend a little bit of time going through combinatorics and counting. So thank you for letting me know, Jesus. So we are going to work on our permutations, combinations, and then after that, we're going to go into probability. Later on, we're going to touch on graphs and proofs and recursion and all the good stuff. So in this week, let me share screen. We're gonna break the chapter 8 into 2 parts only because I feel that there's the going through the materials is gonna help you get a solid understanding of how combination works, and it's gonna help you in the probability area. And so today I'm gonna walk you through the Unit 4 assignment. Then on Wednesday, we're going to do the lab with permutation, and you can see how that would work with C++. It's a little bit different than what we've done last week. I also open a quiz review game, and this is a way that you can pre-test the quiz, right? See how the questions would be asked, and so forth. So check that out. And if you are the highest winner or the highest person, the highest score in the game, I will send you an e-gift card. Okay. But don't forget that you have a quiz that's due by the end of the week. So if you wanted to take care of that later, that will be fine. And it basically covers all the chapters that we have gone through, which is 1, 2, 3, and 7. Okay, so I'm going to go ahead and get started. You can download the notes from the notes page. And then you can also download the assignments from the assignment page. Okay, so in this week, we are going to work with counting. And just to really define combinatorics, it is a branch of mathematics that would work with discrete objects for the counting for different aspects of computer science. So we will take a look at how combinations work. So for example, right, I teach quite a few cybersecurity courses, and we touch on brute forcing a password. And when you brute force a password, you would use different combinations of characters and numbers and symbols trying to match up what could possibly be the user password. Now, the brute force tool or the software application that we use is written by developers, right? Or people who created these tools, they use programming language to build these tools. So with that, you would see that type of application. Also, we would see how we would look at things in combinations, especially when you're looking at like an app for menu order. So we will start with some example like that. If you visit a restaurant and like Chili's or, one of those mainstream franchise restaurant, you would see that they would give you options in combinations. Like you can choose 2 entree and a dessert, or when you do a combo meal at McDonald's or one of the fast food restaurants, right? And ultimately, the programming side of that, we're going to have to take a look at how the variations of the combinations would be, right? And then on the business side, they would determine the pricing and how the analytics part would work into what their profit margin would be. So for us, we would start with the very basic, which is to really define counting. And in solving the problems from the software side, we wanted to look at counting as possible solutions and how we would enumerate through those solutions or finding the optimal solution for the candidate set. And last week we talked about set as an unordered group of values or, objects. So in this case, what we would see is we would work with a collection of discrete objects. And we simply store that into a container when we write the program. And then based on that, we would have a subset that would represent choices that would generate from that collection. So like I mentioned before, if you're looking at brute forcing a password, then, different password that's being used in different iterations is just a subset of the characters that are being implemented or encoded for that particular type of software. So now what we would see is that when we're counting the objects, we would then generate these choices. And there are some rules that would be applied in how we would look at combinations and permutation. So the first example that is shown here is that Alice orders a soup, she can order a soup or a sandwich. And on the menu, there are 6 types of soup and 12 types of sandwiches. And you often see this at a restaurant, right? But to make her choice, she can choose either one of the 6 soup or one of the 12 sandwiches. So in this case, we would have one selection from 2 groups. Okay, so Alice can pick a soup or a sandwich, and we know that there's 6 types of soups and 12 types of sandwiches. So in this case, when the user or when we have to make one selection, right, out of the 2 groups like this, we would apply what we know as a sum rule. So in this case, she would have 6 plus 12 because there are 6 soups and 12 sandwiches. That gives her 18 variation in the meals. Okay, that means that she has to decide one out of the 18 variations. So like a turkey sandwich with broccoli, cheese soup, etc. Okay, so Alice's choice would generalize using a sum rule, and in a sum rule, if A and B are disjointed finite sets, which they are here in the example, then the number of ways of choosing a single element from A or B is the absolute value of A union B. So that means that we would take the cardinality of A plus the cardinality of B. Okay, and cardinality we covered last week, which is the total number of elements in that set. And because it is disjointed finite set, then we would add the cardinalities of those sets together. So in this case, I have 6 for the soups and I have 12 for the sandwiches. And when I add them together, I have 18 type of meals with soup or sandwich. So the sum rule is applicable when one must make a choice from the union of 2 or more sets of alternatives. We need to know what a sum rule consists of and when to apply the sum rule for many questions on our future quiz and exam. So make note of this. You can find this on the first page of your note. So now if we look at the next scenario, we have Bob, and Bob orders both soup and sandwich. And so in this case, he can pick a soup and a sandwich. And we also have 6 types of soup and 12 types of sandwiches. So he must choose one soup and one sandwich. Okay, so in this case, Bob has to make 2 consecutive choices from both of the groups. And so he has 6 ways to choose the soups and 12 ways to choose the sandwich. And we can pair, right, the soup and the sandwich together, which allows us to have 2 consecutive choices. That means that we need to apply what we call a product rule. So we would take 6 times 12, which gives Bob 72 total different meals that he can order from that menu. So now if we throw in a drink for Bob's case, where if we have 8 possible different beverages that he can choose from, then you would have a soup, sandwich, and a drink. Then you would multiply the cardinalities together, which gives him 576 variation in meals with soup, sandwich, and drink to pick from. Okay, so in such case, we would apply the product rule. And in the product rule, it says that if A and B are finite sets, then the number of ways to choose an element from A and B is that we would take the cardinality of A and we multiply it by the cardinality of B, which gives us the variations in the choices. Okay, any question with this? Okay, so let's take a look at your assignment. And in the first question, it asks you, when is sum rule applicable? And the sum rule is applicable when one must make a choice from the union of two or more alternative sets. So in the example, we're only looking at two sets. One set is the soup and the other set is the sandwich. But we can also have more than two sets, right? Like when you go shopping and you need to buy groceries, okay? Then you wanted to put together a meal with the type of ingredients. Then you can look at the variations in meal in the output of the meal based on grouping up different ingredients. Now, the sum rule can be generalized to more than two sets with alternative. And as I mentioned, we want to be able to implement this when we're working with two or more sets. And we would add the cardinality together when making only one choice from those sets. Okay, and that's the true difference between the sum and the product rule, is that sum rule, you have to make one choice. With the product rule, you can make consecutive choices. Okay, any question with this? Okay, so similar to our example, let's try to solve number 2. At the movie theater, there are popcorn, candy, pretzel, nacho, and 5 types of soft drink. You decided to select an item and a type of soft drink at the movie. So in this case, we have to make two choices, a snack and a drink. Okay, so we have 1, 2, 3, 4 types of snacks and 5 types of drinks. So in such case, it asks us, how many choice combinations do you have? So in this case, we would use the product rule because we have to make two choices out of the two sets. There are 4 types of snacks and 5 types of soft drinks. So that means that we can have 20 different combination of snack and drink to pick from, right? You can pair them up differently, and with that, we would have 20 different combination of choices. Okay. Now, let's say that we would only afford one thing. We can either buy a snack or a drink, right? If you've been to the movie, you know it's also so expensive. So if you have to make a decision between a food item or a soft drink, how many choices do you have? So in the scenario B, we have to use a sum rule because we're only making one choice, right, out of the two sets. So in this case, we would use the sum rule, and we would take 4 types of snacks plus 5 types of drinks, which gives us 9 choices to pick from. So I can pick a nacho and be done with, or I can pick a Coca-Cola and be done with but I would have 9 options. Excuse me. Any question? So you will see a similar question to this on our future quiz and tests, and you want to look for the keywords and what it's asking, right? So if it's asking you to make consecutive choices from the sets that's given, then you use the product rule. If it's asking you to make a choice from the sets that's given, then you use the sum rule. Then for scenario C, it says that if you decide to select 2 food items and a soft drink, how many choices do you have? Now this one is tricky, right? And let's assume that we cannot pick the same type of food, right? I cannot have 2 nachos. Maybe I can have a nacho and a popcorn, right? Let's say that they have a special and you can pick 2 food items, but they cannot be repeated. They have to be unique. And we need to pick a drink. So in this case, we still use a product rule because we are selecting, we have 2 choices or more, right? So we have 2 choices, one from the two food items and then our drink, so 3. So we would have 4 types of snacks. So you start with 4. Let's say that you pick popcorn. That leaves you 3 for the next round. Then you would multiply that 4 by 3 because your options is down by 1. So at that time, you have nacho, pretzel, and candy. So now you only have 3 left for the second round of the food. Then that would make you multiply it by 3 for the type of snacks that's left. And then we can pick our drink, which is going to be 5. So when you multiply these together, 12 times 5, that gives us 60 variation in the combination of the choices. Okay. And this kind of lead us into permutation a little bit in that we cannot reuse one of the selection that we previously used, right? We cannot put it back. Once it's selected, it's out of the choices that we can choose for the future round. Okay? So in this case, what you have is you have 4 times 3 times 5, because 3 is because it's 1 less. You already picked that option. So we remove that where it will be reduced by 1. So it will be n minus 1. Okay, any question with this? Okay, as we already covered in the first part, you have the product rule, and it asks you, when is the product rule applicable? The product rule is applicable when one must make 2 or more consecutive choices from the sets of alternatives. Okay, so in this case, we saw that with the movie theater exercise that we just did in number 2 for A and also for C. Give me 1 second. So for the future quiz and test, we need to make sure that we know how to use the product rule when it is needed in combinatorics. Any question with this? And you don't have to type it out like how I typed it. I just want it to be detail oriented so you can see, right, which rule is applied and the calculation. Okay, so we will find the product rule information also on our notes. This is on page 1, along with the sum rule and the example. And then going into page 2, so before we answer the next question, let's take a look at this example. Example 8.1 on page 2. So personal identification numbers or pins are entered onto the numeric keypad. And pins on the office locks are required exactly 4 digits. how many different pins are possible. Okay. So let's say that we have to guess the pin to be able to unlock and go into the office. And you see pins being used for ATM machines and things like that as well, right? So first, you need to take a look at that set, okay? And pin numbers use 0 through 9, okay? So we would have 10 in that set as cardinality. And each pin corresponds with an element. So that would mean digit, 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 digit. Okay. And in this case, we can reuse the number. I can have 1111 or 2225, etc. Right? So because there are 4 digits, that means that there are 4 consecutive choices in the number from the set. Okay, so I can pick a 0, right? I can pick a 1, I can pick a 7, and I can pick an 8. So each selection comes from the set of 10. So that means that we need to apply the product rule here. And since that set is the same every time, that will be the same as saying that from the set of 10, we're going to choose 4 times. So that will be 10 to the 4, which is equal to 10,000 different pins. And if, let's say that we have to use 7-digit instead of 4-digit, you would do the same thing. There is 0 through 9, which is the set size is 10 or cardinality is 10. That will be your base, your base number here. That's 10. And since it's 7-digit, there's 7 selections from that set. So we would need to raise it to the 7, and that gives us 10 million. Okay? Following so far, any question? Okay, now for question B, it asks, how many different 4 to 7-digit pins are there? And so if we're looking at not reusing a certain digit at a certain position, okay? Like we would start with 7 with just the first digit would be 0 through 9. And once we select that and we don't put it back into the group for the next selection, we would then reduce it. So it tells us that a single pin has either 4, 5, or 6. So we're looking at number 4, number 5, number 6, or number 7 digits. Okay, only those. So I can make something like this, 4, 5, 6, 7, right? And then I can do 4, 7, 6, 5. Okay, and so on. That's what it's saying. Okay, so in that case, we would use the product rule to separate the count of the sets for the 4-digit, the 5-digit, the 6-digit, and the 7-digit, and then use the sum rule to count the union of the 2 sets. Okay, so the number of the 4 to 7-digit pins, in this case, we would add them up. So first, that will be 10 to the 4 plus the next, which is the 5-digit, 10 to the 5th, right? 4 choices, 5 choices, 6 choices, 7 choices. Once we have the product of those, then we add them up together, which gives us a little bit over 11 million variations in the pin, especially looking at 4, 5, 6, and 7 digits. Okay. So I can have 4-digit pin, I can have 5-digit pins, I can have 6-digit pin, I can have 7-digit pin. That gives us this. And to really apply this into the real world, I'm going to tell you this, right? If you ever register for an account online, they tell you you can create password between 8 to 12 characters, right? And if we're looking at how many passwords that the user can create from 8, 9, 10, 11, and 12 characters, right? You simply do what? The alphabet would be 26. Let's say if we're using only A through Z, there's 26 character. And if we're only making them do letters only, right? And then plus you also have numbers 0 through 9, which is going to be 10. Okay. And then if you throw the symbols in there, that set is going to be larger. So let's say that if we ask the user to make 8, 7, 8, 9, 10, 11, 12 characters passwords from just letters and numbers, our cardinality for just that is going to be 36. Okay. So for the 8 characters, that will be 38 raised to the power, or the 36 raised to the power of 8. Okay. And then if you're looking at 9 characters, that will be, I can't type today, sorry, 36 to the power of 9 and so forth. And so if you're looking at the total number of passwords that the user can generate from 8, 9, 10, 11, 12 characters, then you add them all up together and you would have a total, okay, that they can pick from, okay. So from somebody that's trying to brute force the password, that's the number of variations that I have to try to get at least one successful attempt. Okay. Any questions? All right. So now let's go to the next example. And that kind of lead us to what we were talking about with the passwords. So passwords are alphanumeric characters. That means that we can do upper lowercase A through Z and then 0 through 9. Okay, and we're not adding the symbol. So if we are to create 4-character alphanumeric passwords, right, and if you use upper and lowercase for case sensitive, then how many of the password are there? Okay, so we would start with 26 for the uppercase letter, capital A through capital Z, 26 for lowercase letter, lowercase a through Z, 0 through 9, that gives us 10 digits. So we need to add them up to really see what is the set, okay, the cardinality of our set. So 26 plus 26 plus 10, that gives us 62 characters in that set. And if we're doing 4 characters, then we would have C times C times C times C. That means we're going to do 62 to the 4th power, which gives us a little bit higher than 14.5 million. So 14,776,336. Okay. And that's just using 4-character upper lowercase and numbers, alphanumerics. Now for B, a hacker has a code that can try out passwords in the system, and this is rated at 1 per second. How long would it take her to break into the system? So for the 4-digit passwords, if it's numeric only, we would have 10 to the 4, and that is 10,000 seconds. Which if you calculate that out, that would be approximately more than 2.5 hours. And one per second, you know, I test this with some brute force software, and 1 per second is very slow. That's like old system, okay? Because to break up a 5-character password, it can be done less than 20 seconds. So, and you know, even on the slow system. So if to use for character that's case sensitive and alphanumeric, then we would take what we found previously, multiply it by the seconds, and so that gives us 171 days, 32 minutes, and 16 seconds. And in security, I tell my students all the time, we're buying time, right? It's if they have time and resource, they can break anything. So in this case, you would see that if they have at least, right, 171 days to attempt without getting caught, then they would still break the password. Any question? All right, so let's answer the next one. So to open a combination padlock, you must use 3 numbers, 0 through 40. How many combination of the numbers can you use? So our first thing that you need to do, the first step is to look at the set size or the cardinality. So the set of numbers, your n is going to be 0 through 40, which gives you 41 for cardinality. And if we are not reusing the digits, let's say that it doesn't allow us to reuse that number once we select it for the 3, then you would use the product rule. You would start with 41 and then take 1 out, then you would multiply it by 40 for the next number. Take 1 out, and then you would multiply it by 39 for the following number, which gives you 63,960 variations of 3 digits numbers or 3 digits lock combination. Now, if we are reusing the numbers, right, I can have 555, right, or 40, 40, 40. Then it becomes 41 to the third, which gives you 68,921 variations of 3-digit number padlock combination. Okay, any question? All right. So since we already did the other example, let's look at number 5. An attacker is using a brute force software to guess your password, which has 7 case-sensitive alphanumeric characters. How many different passwords must the software attempt? Okay, so going back to the example that we just talked about, if this is alphanumeric, that means that we have 26 uppercase letters, 26 lowercase letters, and 10 digits for numbers. So our character set contains 62, right? Or the size with the cardinality is 62. So to approach this type of problem, like I mentioned in the last one, you need to first establish the cardinality of that set, and that's going to help you moving forward. From there, what we need to do is go back to the question, and it tells us that there are 7 characters that's being used. So we simply take the cardinality, which is 62, and we raise it to the 7th power because there are 7 characters for the password. And so this is going to be, you can plug it into your calculator, the scientific mode, okay, and you can see the value there. Okay. Now, that's the total number of variation of the passwords in alphanumerics for 7 characters. And if we try to calculate that out in time, what we can say is that if, let's say that the system runs that code to guess one password every half of a second, then you just multiply it by 0.5 seconds and then convert it to minutes, hours, days, etc. Questions? Okay. Like I mentioned before, you might see a question like this on the test or quiz. So make sure, to understand how to find the cardinality of that set. When it talks about alphanumeric, think about upper lowercase and number. Okay, no question on this?
Easy.
Yeah, this is piece of cake. This is actually fun. This is my favorite part in the class, and the next one, the probability one. And, and why is this really important for you in development, right? You are going to solve problems when programming, okay? That would require you to think about these things. And if you know how to approach using mathematical rules, okay, it should allow you to be able to solve it, okay, from simple to complex problem. And you would start taking pieces out and be able to say, okay, this is how I would approach it. Okay. And just to let you know that I get a lot of feedback from students that transfer to university. A lot of university do coding camp with discrete structure. So they will give you questions like this and expect you to program it, okay? So you have to start thinking about, okay, so how would I be able to solve this in C++ or Java or, and interview questions require discrete math as well. So, okay. To continue from the last one, and it asks you for B. If you decided to use symbols, right, and they allow 16 symbols on the list, not all the symbols are accepted because they don't want SQL injection or other form of injection for the website, and then they would use input validation to control the user input, so that way it doesn't accept the symbols and certain characters, right? And so in addition to the alphanumeric, we're going to throw in 16 symbols. How many attempts will the software try to guess if you're using 8-character alphanumeric password with symbols? So earlier we came up with 62 before the symbol for our set cardinality. Then we're going to add in 16, which gives us 78 for the cardinality. So now your cardinality with the symbol is 78 characters. Then because it's 8-character alphanumeric, then we would raise it to the 8, which gives us this output, this result. Okay. So to be successful, at least one of those, right, would be the password. So as you can see, why do people say that make your password longer and more complex? It's because, right, when you raise it by 1 character and throw in the symbol, look at the value of the total in the variations. It's much higher. And again, like I said, we're buying time. Okay, so for C, how long will the brute force software take to guess the password from question B if the system takes 0.5 seconds to enumerate a password? So it has to attempt at least this, right, to get a successful attempt. So we would take that as the number of attempt multiplied by 0.5 seconds. And you don't have to convert it to days and minutes. I just wanted to show you that so you can see how long that would take. And so this is the seconds, or you can just take this and divide it by half, which gives you the number of seconds. Either way, multiply 0.5 is the same as divided by 2. So you would have this many seconds, and then to convert it to the minutes and the hours, you take that divided by 60 for the minutes, divided by 60 again for the hours, and then divided by 24 for the day, and divided by 365 for the year. So we're looking at about approximately this long if it takes 0.5 seconds to try each password, right? But the system is faster than that. We have much faster processor now, so it doesn't take 0.5 seconds. Take a lot less. Okay. And if you're looking at like Cane Enable, that's the software that we use to brute force. It actually gives you the estimate on the GUI, on the application interface itself, and it tells you how long is it going to take to crack that password. Okay. And it will tell you like 2 years and so many days. And basically this is the calculation that goes into that software.
Professor?
Yeah.
What about the software where they limit the amount of tries? Could they still use that software?
Yeah, so in most cases on the server, we would do an account lockout. Like you see this on for, paying bills online. And if you put in your password wrong 5 times, it locks you out for an hour, right? So yeah, they can set your account lockout, or they can, so basically if you fail 3 times, it's a setting that they put on the server. And they just check that box. And once they check it, right, if it's successful attempt, it's fine. But if you have, 3 or more unsuccessful attempt, it just locks you out for a period of time, or it forces you to reset your password. And what does that do? It just buys them time to look at the issues, or at least if someone is attempting it, it's not you, that person, hopefully the owner of that account would realize it, because they would receive an email or something like that that says that somebody is attempting to log into their account or resetting their passwords. And security measure is only, as it would be implemented. It's never 100% foolproof. But from the end where we would see how this type of application would be used, it's used all the time. It's used to crack software, it's used to hack account, it's used to circumvent wireless, it's used to break encryption. Encryption key, they brute force that too, using aircraft. So, so now you guys have a picture of how this is done, and that will equate out to time. For D, it says, suppose the password may have 8 case-sensitive alphanumeric characters and must contain at least 1 digit and at least 1 letter. You know how they require that as part of your password that you create. How many are there? So we have 62 characters, right, with alphanumeric, and there are 8 characters, so we would raise that to the 8. And that will be our alphanumeric characters with no restrictions to start. But of these, this is when we use inclusion-exclusion principle now, okay? Of these, we would have 52 to the 8 are consisted of letters only, okay? Because why did I get 52? It's 26 plus 26. Uppercase is 26, lowercase is 26. That makes it 52. And 52 to the 8, that will just be 4 letters. Now, if I'm looking at digits only, that will be 10 to the 8. That will be consisted of digits only. and all the others have at least one digit and at least one letter. So what you have to do is you have to start with the total variation of passwords for both, right? For letters and numbers, you include those. Then you're gonna exclude, the letters only and the numbers only, which gives you the leftover, which are these, okay? And this is when we apply the inclusion-exclusion principle. We include the total, we exclude the criteria, which is letters only or number only. And we have what's left. Any question? So future exam and quiz have these type of questions. You're going to be allowed to use scientific calculator for the final exam, but you have to know how to look at the problem and be able to solve it, right? How to approach it, be able to solve it, and then you would select the answer based on the option that you see. Okay. So now let's touch back on the notes if you don't have any question for me for number 5. We don't have much to do today, just doing these. So all right, so we already looked at this example on passwords, and then it goes into the bit strings with 0 and 1s, right? If there's 8 bits, that will be 2 to the 8th because there's 0 or 1s, right? So that will be base 2 raised to the 8th, which gives us 256. How many bits are with 16 bits? So that would be 2 to the 16, which gives you 65,536. So in my other class, we looked at word size this week for CIS7, and we will look at the variations of the memory allocation for 16-bit. So that would be the same calculation there. And then solving to determine the largest integer that can be represented with 16-bit 2's complement. So you would have 15 places that represent the magnitude of the integer, and you need to subtract 1, which gives you this. Okay, so it gives you the explanation here. Let's do the next example so you can work through your assignment because it's very close to that. Okay, so there are 3 sections of this class, and we have 73 students in one, 64 students in the second section, and 41 students in the third. And it asks you how many distinct ways are there of choosing one student to write up notes for everyone to use for the final. So in this case, we're choosing 1, and that should give you a hint on which rule to use, right? We would use the sum rule. So we would take 73, that's for the first section, plus 64 for the second section, plus 41 for the third section, which gives you 178 possibilities to pick one student from all three classes. Now, question B says, how many distinct ways are there to choose one student from each class, right, for the advisory committee? So we would use the product because we would have consecutive choices from the sets. So we would take 73 times 64 times 41, which gives you 191,552. And then the next question, it asks you how many distinct ways to list 6 different students from the 41 section class to go on the board one after another to present the problem. And in this case, we have to permutate because once the student is selected to go to the board, they're out of that set, right? That person is removed from the set. And then the next student. So we would start with 41, and then we reduce one student. We would multiply it by the next set that's left, which is 40, and then multiply it by 39, which we took out 1, 38, 37, 36. And we stop here. How do I know when to stop? There are 6 rounds for 6 students. So 1, 2, 3, 4, 5, 6. So with that, we would stop after we pick the 6 students, and that would give us this many. Okay. And it says here that this is an example of permutation. And permutation is that we don't recycle that choice. That means we don't put it back into the set to be reselected. Where combination, you got to be careful because combination itself is reusing that option. With permutation, it doesn't, right? We remove that from the set once it's selected. And then in the next part of the example, if we need to pick 6 students to form the volleyball team, and in this case, we would then take the total of 3 classes, which is 178. And as we pick each of the student, we need to apply permutation as well. So 178, 177, 176, and so forth. After we pick the 6, we would use the product rule because there are 6 choices in that set. Okay. And so with this, that would be each of the 6 students appear in the list. That will be a factorial of 6. 6 times 5 times 4 times 3 times 2 times 1. Okay, so the set is 6 students of 178. Okay. Now, let's look at the next exercise. Number 6 on your assignment. There are 3 groups of audience, 30 people in group 1, 40 people in group 2, and 50 people in group 3. The first question asks you, how many distinct ways can a person be selected from 3 groups to win a prize, right? We're picking one person from the 3 groups to get a prize. So this one, that will be a sum rule because one choice. So 30 plus 40 plus 50, which gives you 120. Now for question B, it asks you how many distinct ways can a person be selected from each group to meet a performer? So we are picking one person from each group. That means that we have 3 choices, right, in the scenario B. So we would have 30 times 40 times 50, which gives us 60,000 ways that we can pick 3 people from 3 groups. And for case C, how many distinct ways can 5 people be selected from group 3 to win tickets for the next event? We don't want people to win ticket twice, right? So once we select them, we remove them from the set. So out of the 50, group 3 has 50 people. So that's our beginning cardinality. So you would take 50, and then once the person is selected, you would have 49 left. So you would multiply it by 49, reduce 1, multiply it by 48, reduce 1, multiply it by 47, reduce 1, multiply it by 46. And we stop here because you have 5, right? For 5 selection. So you have over 554 million ways to pick 5 people from group 3. Any question with ABC for number 6? Okay, let's answer D. How many distinct ways can 5 people be selected from all groups to win backstage passes? So we would start with looking at the total, right? 30 plus 40 plus 50, that gives us 120. So the first person that's selected would be from the set of 120 people total from 3 groups. We take that person out, then we would have 119 left. Then we take another person out, we would have 118. Take another person out, we would have 117. Take another person out, we have 116. So we stop here because that gives us 5 selection. And so this is what we have as the result for the variations or distinct ways to pick 5 people from all groups to win passes. Okay. So let's talk about inclusion-exclusion principle. You saw a little bit of this with the example that we did with the upper lowercase and the alphanumeric characters. Inclusion and exclusion principle, you would start with using a sum rule, right? And we would assume that the sets of alternatives from which one must make a single choice, that would be the first part of it, and it would be mutually disjointed. It does not share any common elements. In situation that one single choice must be made from the sets of alternative that's not disjoint, in the example where you would see with Alice and Bob for the lunch menu. So we would add up the sum of the sandwich choices and the soup, okay, as they are disjointed. But if they're not disjointed, then you would look at it as a double count, okay? So we don't want it to be double counted. That's when we would subtract the overlapping options to get the corresponding sandwiches that are double counted. So we got to exclude those. Okay. So just like what we talked about, once we select the person that won, we wanted to remove them from the group, right? But if we are looking at things that could be overlapping, that could be double counted, then we want to make sure that we subtract that. Okay. So when we're looking at set A and set B, as they are not disjointed, they are jointed, then this area in the red is double counted. So when we add it up, right, the sum, that would include everything, including the double counted area. So we would then need to exclude those by subtracting the differences. Okay, when we worked with Venn diagram last week, you saw a little bit of this already. So in the inclusion-exclusion principle, in the finite sets, you would have set A, cardinality of set A plus cardinality of set B, subtract the intersection of A and B. Okay. So the example that we can see here is that if we have 6 uppercase letters to start with A and end with C, how many strings do we have? That will have 6 uppercase letters that starts with A or end with C. So we would have 26 to the 5th that starts with A, right? Because we would start with A and end with C, so that will be 5 selection from that set that starts with A. 26 to the 5th that ends with Z, and 26 to the 4th that start with A and end with C, and they are counted twice. So you would take 26 to the 5th plus 26 to the 5th, subtract 26 to the 4th, which gives you the result. Okay. So let's take a look at this one. Let's see. Okay, before we do number 7, because we only have, let's walk you through it. Okay, let's do number 7 together then. 7. To use the inclusion-exclusion principle to determine how many positive integers between 100 and 987 are inclusive. Okay, so first, the problem gave us the range, which is 100 to 987. Okay, so first we need to determine the cardinality of that set. Okay, so you take 987, subtract 100 plus 1, you would have the size of that set, which is 888. 888. Then it asks us how many positive integers between 100 to 987 that's divisible by 8. Okay. And we can say that every 8th digit is divisible by 8, like 8 can divide it by 8. 88 can divide it by 8, right? So every 8th digit is divisible by 8. So you would take the set and you would divide it by 8 to give you the number of positive integers that are divisible by 8, because it's every 8. Okay. So in this case, we would take the set divided by 8. If it asks you divisible by 10, then you just take the set divided by 10. Okay. Any questions so far? Then for B, it asks you how many positive integers between 100 to 987 are even, okay? And every other number is an even number, right? Like 2, 4, 6, 8, 10. But in this case, we start at 100, so 102, 104. So every other number. So we start with the set size, or cardinality is 888. And we would divide it by 2, which gives us 444 integers between 100 to 987 that are even.
I'm just curious, why did we add 1 in for number 7 again?
Because you got to count the 100. Because if you subtract 987 minus 100, you exclude the 100.
Okay.
Because you start at 100. You count it. That's your element 0. You're welcome. Okay. Then we found that there are 444 numbers that are even in this range. Okay. And that's easy. We simply divide it by 2. Right? 50 odd, 50 even. Okay. And then for the next question, let me move this up. It asks us how many positive integers between 100 to 987 that are distinct digits. Okay. So here's my explanation, and I typed this out. So integers between 100 and 987 have 3 digits, right? Agree? We are in 3-digit range. Anything below 100 is less than 3 digits. Okay. The leftmost digit cannot be 0. And that we see because it starts with 1 and it goes higher, right? Like if you count up, this is why they call it counting. If you count up, right? 100, 101, etc. There would never be a time that it would go back to 0. So it cannot be 0 for the first digit. Okay. And so that means that there are 9 choices, because if you're looking at 0 through 9, it cannot be 0. So that will be 1, 2, 3, and so on, 1 through 9, right? Because 1 through 9. Okay, for the first digit in the 3. And with that, we would have the second digit can be any digit but the first, because it asks for what distinct digits. It cannot repeat the 1, or it cannot repeat the first digit. So that also means that there are 9 choices. Okay. And once we remove that, there would also be 8 choices for the third digit, because we're looking for distinct digits, not repeating digits. I cannot have 111. No, that would not count for the case C. Okay, I can have like 1, 2, 3. Okay, and so the 3 digits have to be different from 1 to the next in the 3. Okay, so I can have like 6, 8, 7. So in such case, then now we have established how the digits would be for each, the set that would represent the digits. Then we would use the product rule. Yeah, 999 is out of range. 999 isn't a valid number for this problem because the numbers are the same and not unique. So you cannot have 999 because 987 is the max. It's out of range. Okay. You can't have 111 You cannot have 1, 1, 2, 2, right? So the digits cannot be repeating. That means that we cannot recycle that value in that set. So in such case, we would start with 9, right, to represent the first, multiply it by 9 for the second digit, and then multiply it by 8 for the third digit. Because the third digit cannot repeat the other two. So once you multiply that together, then you have the answer for C. Okay, so something like this. I will put this here in case you didn't follow that, but thanks for letting me know you got it. So I can have 1, 2, 3, or 5, 6, 7, but cannot have 1, 1, 2, or 3, 3, 3, or 3, 3, 4, etc. Okay. Cannot repeat. So repetition is combinations. Non-repetitions is permutation. And permutation, you just you just remove that option once it's already been selected from the list, which reduce it to 1 minus or minus 1 from that set each time. Okay. Let's talk about the next one. There are 38 people in the room. How many people would have guaranteed the same day of birth? Okay. And I'm talking about the day, like if you're saying that somebody's birthday is January 2nd, right? The second, the number 2 is the day of the month. And we're just looking at the day of the month. Okay, we're not looking at birthday where it would be the month, the day, and the year, but it would just be the day of the month. Okay. So if you're looking at the total number of months we have, the days that we have in a month, the maximum number of days that we have is what, 31 days, correct? So we would have, or 30, we would 31. So we would have, starting with, we would take 31 minus 1 and plus 1, which gives you 31 days in a month. So for a longer month, we would assume that it would just be 31. There's some months that are less, right? 30 days or 28 days, depending whether we have a leap year or not. Okay, so the maximum number of days in a month is 30 days. Okay, and if this is when it's going to lead you to Pigeonhole principles now. Okay, so there are 38 people in a month. So it is guaranteed that there would be 2 or more people that would have the matching day of the month for their birthday. Okay, like we would say whose birthday is on, like if they go around and they meet each other and they would say, oh, I'm born on the 6th of the month, or I'm born on the 22nd of the month. And there would be 2 or more people in the room because there are 38 people, right? So if you take this and you find a ratio, that's at least 100% plus. So you would have at least 2 or more people that's guaranteed to have the same day of birth or the same day in a month of the month for birthday. Okay. Any question? Okay, so now we already did something like this. So there's some example there where we would look at how we would find the number from what we've seen previously with the range 100 to 987. This is similar to that. So you can take a look at the example as well in your notes in your book. So in Pigeonhole Principle and such that if k plus 1 of more objects is placed in the k box, then there must exist a box that contains 2 or more objects. So if I have 10 holes, right, and I need to put 1 object in each hole, and if I have 11 objects, then that means that I would have 1 hole that has 2 objects, okay? So let's say that if I have 11 present and I need to put those into 10 holes, okay, then I'm going to fill up. So I already filled up the 10 holes with 10 presents. I have an extra left. I have to put that present in 1 hole. So at least 1 hole that's going to have 2 presents. Okay. And this was tested using pigeons, and that's therefore you would hear the name Pigeonhole Principle, that there would be holes for the pigeons. And if you have more number of pigeons, they're going to fill up the hole, and there would be 1 hole that you would have 2 pigeons or more. Just like how we would look at the birthday, how many days in the month, and if there are more people than the number of days, then you would have at least 2 or more people that would have the matching day in the month. Okay. And in this example, it's similar, but it's looking at the birth month. So if 13 people are gathered in a room, and if we're looking at there is any 2 or more people that would have the same month of birth, we would be guaranteed with at least, right, at least 2 or more. But if you have 11 persons that's in a room and you're trying to see if there is a matching month of birth, then there's no guarantee in that. Okay. So any questions so far regarding Pigeonhole Principle? Okay. So I'm going to touch on this example, so that way you can expand on it, but you can also follow through and look at these examples as well in addition. So suppose that there are 102 students in 2 sections of the class. If they all take the final, and will at least one of the student get the same grade? So we saw that there's 102 students. The possibility, right, the cardinality of this set is 0 through 100. That means that there's 101 possible grades if they are different from 0 through 100. So based on the Pigeonhole Principle, there's 102 students in 2 classes, and there's 101 possible grade. Yes, there is at least 2 students that would have the same grade. Okay. Okay, so let's do the red socks and the blue socks example. Example 8:10. So in a drawer, we have 12 red socks and 12 blue socks. And we need to take 2 socks out, a pair. Okay. How are we going to be able to match if we can't see them? Okay. It's like how now whenever you watch game show after this class, you're going to be able to determine the probability. Like, you know, if you're looking at the old or the new game shows on TV, right? If they're drawing prizes out of the bag, opening doors for prizes. Okay, so we'll touch on that when we talk about probability next time. Okay, so all of that apply discrete math. So how many must I pull in order to have a matching pair, right? We have to pull 3 because there are 2 colors. Okay, so in order to get a match, we got to make sure that we take 3. Okay, so whenever that you go to carnival and you're trying to win prizes by pulling things out of a bag or a box or whatever, and you buying those choices, right? You just gotta take a look at the options based on Pigeonhole Principle. Now you can determine, right, how many tries you need to get in order to win. And all of these games, right, they profit because people don't really understand, right, the approach in it. So in this case, if I want a matching pair, I have to pick 3 out because there are only 2 colors, blue or red. Okay. Now, if I have 3 colors, then I have to pull 4, right? And so on. How many must I pull in order to have a pair of red socks? Okay, remember that there are 12 red socks and 12 blue socks. Okay, so you have to be above the number of red socks that's available, and you need a pair. So in this case, we have to pull 14 socks in order to get the red, because you can have 12 that would be completely blue, and then the next 2 would be all just red, because once you remove all the blue, then you have the next 2 will be red. Okay, so you have to have a minimum of the number of the blue socks, and then in the worst case scenario that you just pull the first 12 would just be all blue, and then the next 2 would be red, so 14 total. Okay. And then how many must I pull out to be sure that at least 1 of each color? Well, there are 12 of blue and 12 of red, so you need to pull at least 13. So you would have at least 1 of each color, a red and a blue. Okay. All right. So let's touch on, we already talked about the birthday one. Let's define permutation for number 9. So permutation is defined as an ordered arrangement of a set of objects. And when we look at the arrangement, your choice from the set is not being reused. So once it's selected, it's removed from the cardinality, from the set size. And in permutation, keep in mind that order does matter, right? So when we say something like 1, 2, 3, it is different than 3, 2, 1, or 2, 1, 3, or, and so on. And when we're looking at the digits, okay? So the order of it matters. Any questions? Okay. Let's do the Netflix. So on honesty, I wrote this when I even found out what Netflix really was, because I wrote this questions when years ago, maybe 4 years ago or 3 years ago. And I didn't really use Netflix. My student, they always talk about it. So I always thought that it was like a Redbox thing until later on when I got Netflix. But, think of it like just a way that we would rent movies. So forgive me if it's like a little off there. Okay. All right. So let's assume that you receive 10 free movies from Netflix or Redbox, 5 comedy movies, 2 action movies, and 3 drama movies. Okay. And if you only have time to watch 3 comedy movies out of the 5 options, how many possible arrangement of the comedy movies can you watch? And we can sit there and we can write out, you know, different title arrangement, or we can do the calculation. So we receive a total of 10. But in this, we care about the cardinality for the subset here. So 5 comedy movies, and you're only able to watch 3. Okay. So what that means is I would start with the 5 to start, right? I watch a movie. It's off the list. Then I go to the set, which has 4 options left. I watch another movie. Then that's removed from the list. Then I watch another movie from the 3. Now, because I only have time to watch 3 movies, I stop there. So 5 times 4 times 3, which gives us 60 different variations in watching 3 movies, 3 comedy movies that's given to us. Any question with number 10? Okay. All right. Sorry for the crazy color code. I'm a very visual person. The way I learn and the way I teach, sometimes I highlight things like crazy. So, all right. I know, me too, right? Like just binge watch a bunch of movies, but you know, sometimes I'm very addicted to TV sometimes. And yeah, that just takes up a lot of time where you could do something else. I know. All right. So on your day off, you decide to watch 4 comedy movies, 2 action movies, and 3 drama, right? So we wanted to know how many possible combination of the movies can you watch. So you would start with the comedy, which we calculate previously, but this time we have 4. So 5 times 4 times 3 times 2. As you watch it, right, it's off the list, right? Some people watch it twice, but this is not the case. Once we watch it, it's off the list. So 5 times 4 times 3 times 2, that will be for the comedy movies. I highlighted that in yellow. And then we're going to watch 2 action movies. So since there are only 2, so we would do 2 times 1, which gives us 2. And then we're going to watch 3 drama movies. So 3 times 2 times 1, which gives us 6 here. So when we multiply everything together, we have 1,440. Okay. So that complete our requirement to be able to solve how many variations of comedy, action, and drama movie we can watch with the requirement of 4, 2, and 3. Any question?
Why do we stop at 2 when the first one?
This for the action movies? I'm sorry, I can't hear you. Say it again.
The comedy movies.
For the comedy movies? Oh, because you have 4, right? So I started with 5 because they gave me 5 free option for the comedy. So once I watch one, that's off the list. So that's 1. Then I watch another one from the 4, right? That's off the list. then I watch another one that will be 3, then I watch another one that will be 4. Okay, so because you can only watch 4 comedy, then you just reduce one until you reach the 4. So 1, 2, 3, and 4.
Thank
Yeah.
you.
You're welcome. This is why it's called counting, right? Because if you think about it, you just count down and you would multiply each time. It's really easy. Yeah. So then after I multiply this out, right? This is for comedy, this is for action, and this is for drama. And I have 1,440. Okay. Then for KC, it says if you decide to watch all the comedy movies first, right? Like A, B, C, D, E, and then watch the action movies, how many distinct arrangement is possible? Okay. So we would start with the 5, and earlier, if you recall, they talk about, you know, the permutation versus the combination. And so since I have 5 comedy movies, I'm just going to watch that first because it's in order. Then I would have factorial of 5 times, and then I'm going to watch the next order, the next things in order that will be my action movies, that will be factorial of 2. So 5 factorial is like saying 5 times 4 times 3 times 2 times 1, right? And then we would multiply that with 2 times 1 for 2 factorial. And then you would have 240. Or you can plug in the factorial, use the factorial button on your calculator, it will be the same. Okay.
Professor,
Yeah.
for our 10A, it asks for action movies and not comedy movies. So should we switch the question to say comedy, or should we answer it for action?
I meant to say comedy movies. I'm sorry.
Okay, so just change the
just type it, change in the word. Unless you wanted to calculate it for action, because there, you know, you cannot have 3 choices out of the 2. There are only 2 action movies. So that was boo-boo on my part. I'm sorry if I didn't change it on yours. Yeah, so just change the comedy, the word comedy to action to comedy there. I gotta remind myself to go back and fix the student version of it. Okay. Okay, any other questions? All right. So for 10B would technically be permutation, not combinations. Yeah. This should see the term combination is used loosely, I think, for everybody and everything out there, right? I should say change this to variations. That makes it a little bit unique, because when you say combination, it's repeating the choices, right? It's reusing the choices versus permutation where it's not. And permutation would apply order as well. Okay. Yes, so Jason, you are correct. I just changed this. Just the wording is, it could be confusing. But I've seen a lot of questions that relate to this, and people ask for combination, even in the book, to ask about like combinations, even though they meant for permutation. Okay. So even permutation is under the combinatorics, so sometimes people use it loosely as an umbrella term. But now you can see the difference. Okay. Let me check the notes and see if I make sure. So they included in the notes, there's example 8:11. It talks about every integer for n that is multiple. So you can also look at that example, but sometimes that can be. So with the generalized principle for Pigeonhole, make sure you understand Pigeonhole, the boxes with the object, right? We talked about the socks. We talked about the day of the month for the people in the room. We looked at the example for the students. And then there's also another example that talks about birthday that has the same month. And the definition for permutation. So next week, we're going to pick up on this, and then we're going to look at the actual formula for this, right? So you kind of understand how to apply the product rule and then looking at the Netflix movie in order. But permutation, the key area is that the ordered arrangement of the set of the objects is applied. And also, like I mentioned before, where we don't recycle that option, we don't reuse it. It's off the list. So the author, Dr. Fell, uses errands, and where you don't repeat the same errands when you run it. So like if you need to go buy grocery, once that's done, it's off the list, right? If you need to do a chore, once that's done, it's off the list for that day. So the each permutation, it would have an associated cost. And and in the case, like the example that she uses, the total driving distance of the errands to process a certain order. And when you look at software, if you're looking at the sequence behind it, right? Like for example, like a checkout software, after the customer add everything into cart, okay, and then the next process would be submit for checkout, and then order process, and then put receipts and all of that. But in that, you would have the associated cost because that task is off the list, okay? But each of the associated tasks would be like, contacting the database, updating customer information, processing the PO, converted that to receipts, right? Email it back. So there are additional requirement that's going to be part of that process in the sequence. And we wanted to think about ways to really reduce the associated costs with that. Okay. So here she talks about how brute force approach would be a list of all possible permutations, like what we touch on, and if they're guessing password, PIN number, etc. And to determine each of the associated costs, the pick of the permutation with the least cost. So the effective software tool would reduce the associated costs to the very minimal. Okay, and how is it going to be able to determine that? So the tool itself needs to pick the variation of the password and the PIN that would have the least associated cost, so that way it doesn't take so long, right? But in analysis for software, we always expect the worst case scenario anyway, right? So but in the design process, and that we wanted to really approach it with the least cost. So now, using the same example, it says with the 4 errands to start, then we would reduce each one. And finally, we would have the last errand. And in that, we would use the product rule. And with the counting permutation, oops, I'm sorry. this is what it would look like. N factorial is going to be n times n minus 1 times n minus 2 and so forth until we reduce it down to 1. And so that's why we count down 1 each time. You subtract it 1 each time with the counting permutation. Okay. So Jason, when he mentioned that really, this section is what we should refer to when we're looking at 10b. And so the formula that would apply to next week exercise is going to be on page 9. And you can take a look at this, but I'm going to come back to this starting next week on Monday. We will address it with the assignment for next week. And this week, we're going to, on Wednesday, we're going to do the lab that's going to be correlated with permutation and combination. And then we're going to take a look at how that would be following this. So in the choices that we make for the permutation, so if we choose R is going to be our choice, right? We're going to pick R out of N. Okay, N is going to be our set. So to start, we would take the cardinality and we would make it into a factorial. So factorial of the N divided that by N minus R factorial. And this would be the number of R permutations of the N distinct elements. So out of the N set, we are selecting R out of the N. Okay. So if you're looking at the errands, right, the list of errands, N is 4, right? And if we need to choose one errand to run because that's all we have time with, the R would be 1. Or when we're looking at the movies that we talked about, 5 of the comedy movies, that will be N. And if we can only watch 3, then that will be 3 is the R. So we would apply this into the formula. And for 814, it talks about a wedding party. I'm going to go over, and this is the last one that I'm going to go over, and then we'll finish the session. So in example 814, it talks about a wedding party, right? We have a bride, a groom, the in-laws, the best man, maid of honor, ushers, and bridesmaid. Okay, so we have a total of 12 people at the party. How many ways are there to arrange all of them in a row for the picture, right? Photographer stands there, and then we need to arrange bridegroom in the middle, left or right, right? And then the people around them. So we wanted to look at the variations of arrangement for the picture. So here we have 12 people at the party, and we are going to pick 12 out of 12 to take the picture. So we would have 12 factorial ways to arrange them in one row, right? So we would do 12 times 11 times 10 and so forth. Now, for the scenario B, how many ways if the bride and groom stand together on the left side of the line? Okay, so if we put the bride and the groom on the left side only, that would give us 2 ways to arrange the bride and groom on the left side. Okay, so remove the bride and the groom, we would have 10 out of 10. And so that will be factorial of 10 for the rest of the people to arrange. Okay, so now because we have 2 ways to arrange the bride and the groom on the far left side, so that means that we would have 2 times 10 factorial for the possible arrangements. Okay, because 10 factorial is for one way, and then another 10 factorial is for a second way. So that will be 2 times 10 factorial. Then we would look at the ways of the bride and groom together anywhere in the line. Okay, so with that, that would also be, we started with 10 factorial because that's for the other people that's at the party to arrange without the bride and the groom. And then we can have the bride and the groom together between and between the lineup of the people. So the left or the right. So that would give us 11 positions because that's going to be 10 plus 1 for the groom or 10 plus 1 for the bride. And there would be 2 ways to arrange the bride and the groom, right? Because there are 2, bride and a groom. So you would take 10 factorial times 11 for the 11 different position times 2. And then lastly, how many ways can 5 members of the wedding party line up for the picture? Just like what we've done before with the movies, we would start with 12 times 11 times 10 times 9 times 8, which gives you choosing 5 out of the 12. Okay. Or you can calculate it using the formula factorial of 12 divided by 12 minus 5 factorial. Okay, which gives you the same output. Okay, so what I think is look through the examples, and sometimes the wording can be difficult and confusing, but if you start thinking about it, if you draw things out, sometimes I create boxes so that way I can look at the arrangements. If that helps you, then that will be good. But look at the example, go through the chapter, do some practice, and try it out. And then we will pick up from here. We're going to go more into differentiate combinations and permutation more, and then applying the formula next Monday. But for Wednesday, we will do the C++ lab, and I already released that on Canvas. Okay, any questions? Okay, so go ahead and type in your name in the chat box in case I don't get your attendance. And if you have any questions, I'll stick around for a little bit, and have a wonderful night if you don't have any questions. See you Wednesday. Good night. Thank you. Good night. Let me stop recording so